What is quantum mechanics, you ask? Well, it's the science that attempts to explain the phenomenon that is most noticeable within particles smaller than atoms. Quantum mechanics isn't just the physics of small things, it's a complete improvement of Newton's mechanics, how chemistry occurs, and just a new way of thinking on how the world really works. One of the phenomena of quantum mechanics is the photoelectric effect.
Our adventure into quantum mechanics begins with introducing the brilliant minds behind the photoelectric effect.
The photoelectric effect was first discovered by Heinrich Hertz in 1887. It goes something like this. When you connect a battery to two zinc plates enclosed in a vacuum, you can send an electric current through the empty space between the two plates without the use of a wire. You can simply shine a light on one of the plates. One of the plates is connected to the negative terminal of the battery and the other is connected to the positive. If you shine a beam of light only on the negative plate, a meter hooked to the circuit will show that an electric current is flowing.
Using the classical Maxwell wave theory of light, it was believed that the more intense the incident light, the greater the energy with which the electrons are ejected from the metal. That is, the average energy carried by an ejected electron should increase with the intensity of the incident light. In truth, German physicist Leonard found that this was not actually the case. Through experiments, he found that the energies of the emitted electrons were independent incident radiation intensities.
The classical view on light was that it behaved as a wave, yet Einstein in 1905 successfully resolved this paradox by proposing that the incident light consisted of individual quanta, called photons. These photons interact with the electrons in the metal like discrete particles rather than as continuous waves. For a given frequency of the incident radiation, each photon carries the energy, which is E photon equaling Planck's constant times frequency. Increasing the intensity of light increases the number of incident photons per unit time, while the energy of each photon remains the same.
These brilliant minds paved the path to what we now know as the photoelectric effect. In modern-day quantum mechanics, the photoelectric effect is explained by a phenomena that occurs when light of enough high energy strikes an object. When light strikes the object, it emits electrons. Now, whether electrons are emitted or not depends entirely on the energy, not the intensity of the light. What this simply means is that it does not matter if the light is bright or dim. What matters is the frequency of the light. So if blue light is needed for the emission, a dim blue light can cause a photoelectric effect. But if a red light is used, it will not cause any emission whether a dim or bright source is used.
This emission of light is due to the frequency threshold. The frequency threshold is where every metal responds to a certain frequency of light at which it releases electrons. If the frequency of light is below the metal's threshold, it won't release electrons, which is the red light. But as soon as the frequency level is high enough, electrons will be released, which is the blue light.
This is extremely important, as it shows that electrons are liberated from an object due to the energy of photons and not the intensity of photons striking the material. What this basically meant was that light was indeed quantized, or arranged in small packets of energy, as Einstein proposed. The photoelectric effect is perhaps the most direct and convincing evidence of the existence of photons. It provides undeniable evidence of the quantization of the electromagnetic field and the limitations of Newton's mechanics. The classical understanding of light as a wave didn't account for why the predictions of certain light behaviors didn't match the experimental results. Einstein's explanation of light behaving as a particle of energy instead of a wave produced results that matched the predictions. The main problem with this was that it led to the wave-particle duality of light that everyone struggled to grasp within that time period. The photoelectric effect is important to quantum mechanics because it indicates that light should behave as a particle.
Although the photoelectric effect may be mysterious and quite an unusual concept to grasp, you can easily see it within our everyday lives. Many elevators and garage door systems use a beam of light and a photoelectric device known as a photocell as a safety feature. As long as the beam of light strikes the photocell, the photoelectric effect generates through ejected electrons to produce a detectable electric current. When the light beam is blocked by a person, for example, the electric current is interrupted and the doors are signaled to open.
We hope you enjoyed this small journey into the world of quantum mechanics by discovering the photoelectric effect. We hope you've gained some knowledge, if not excitement, for how the world around you works.